Infrared spectroscopy is the analysis of infrared light as it reacts with a molecule. IR is widely used in lab environments to determine which functional groups are present in a molecule. The molecule being tested by IR can absorb, emit, or reflect light, and depending on the way a molecule vibrates, it can either be IR active or inactive. When a functional group has a vibrational pattern that presents a change in dipole moment, the group is IR active and can be recognized on an IR spectrum. For our experiment, we are using computational methods to create IR spectra of various alcohols for analysis of the hydroxyl functional group. As a result, we plan to make conclusions on the effect of nearby atoms and their electronic contributions to the variance of the hydroxyl groups in IR spectra. To see the effect of nearby atoms on the IR spectra of the hydroxyl group, we decided to test different types of alcohols. We use an increasing chain of alcohols as well as a branched and cyclic molecule. To determine the vibrational frequency in the IR spectrum, we used WebMO as our computational source, MOPAC as our computational engine, PM3 as the theory, a number of 1.006 as the scaling factor, Def2 SVP as the basis set, and vibrational frequencies as the examination.
IR spectroscopy gives us values for frequency and intensity. The frequency gives us information about the mass of the atoms and the force constant of the bonds vibrating, while the intensity tells us about the variance in dipole moment. Since the bond we are focusing on contains the same atoms with approximately the same force constant for all the molecules examined, we didn't expect to see much of a change in their frequency. They were right around 3,900 inverse centimeters for all the molecules. On the other hand, as we increased the length of the carbon chain connected to the hydroxyl group, we saw that the intensity also increased. Going from methanol to ethanol, the intensity increased from 0.1482 to 0.1820. This change is due to the effects of the additional carbon on the polarizability of the molecule. We see that this trend continues for each carbon that is added to the chain. Propanol, for example, has an intensity of 0.1924, and with the addition of another carbon, butanol has the intensity of 0.1933.
When comparing butanol, a primary alcohol, to 2-butanol, a secondary alcohol, the OH stretch intensity decreases from 0.19 Raman to 0.170 Raman. This can be explained by the addition of alkyl groups, resulting in more inductive donation of electrons. This decreases the polarity of the OH group and hence less variance in the dipole moment. Now remember that variable dipole moments are the key drivers of vibrational intensity. You can see that phenol is super intense, with an intensity of 0.2761 Raman. This is due to the fact that phenol has a benzene ring that has high electron density due to resonance. This pulls electron density away from the hydroxyl group, causing vibrations to either have high dipole moments close to the ring or low dipole moments further from the ring. As a result, a high intensity is presented for the OH stretch.
The variance of OH stretching was tested with IR absorption. The molecule bonded to the hydroxyl group was a basis for our test. By using this technique, we were able to determine the effect of nearby molecules as well as substituents. For primary alcohols, increasing carbon count caused the OH stretching intensity to increase due to the increase in hydrogen bonding strength. As the hydroxyl group is accompanied by more electron donating substituents, the intensity decreases due to the decrease in dipole moment. The opposite was seen when the alcohol was located on the benzene ring. As the intensity increased due to the large electron withdrawal from the oxygen, increasing the dipole moment and allowing for stronger hydrogen bonding. Although an intensity varied between the molecules, the frequency of OH stretching remained relatively constant at 3,900 inverse centimeters.